So here we have a classic chasing problem. So it is given that a particle A is moving with a constant velocity u along x-axis. So this particle is moving with a constant velocity. Speed is constant as well as the direction is constant. It is moving in a straight line along x-axis. And particle B moves with a constant speed v such that its velocity vector is always directed towards particle A. So particle B has a constant speed, but its velocity vector will always be towards A. The positions of the particle at t equal to 0 is shown. Let us say at t equal to 0, this separation is d between the particles A and B, and this angle is 90 degree. So we need to find the time after which the particles are going to meet, right? So let us say that since the velocity of particle B is always towards A, so the velocity vector, you can see that at any general time, if the particle A is at this position, then the velocity of B is towards A. So velocity of particle B will always be directed towards A. So we are assuming, let us say this is the point C where the particles will meet. Now, at any general instant, at any general time, suppose this is the position of particle A and this is the position of particle B. Now, the velocity of particle B is always along the tangent to this path that the particle B is taking. Instantaneous velocity is always tangential to the path and it is directed towards this point A. So, suppose you can see that this separation between the particles A and B, this separation is changing with time. Initially, this separation was d, and when the particles will meet, this separation will be 0. So, I have considered that at any general instant t, this separation is equal to small r. Now, what is the rate of change of this separation? What is dr by dt? Rate of change of this separation. You can see that if the angle that this line joining AB, this line joining the particles AB, if this line is making an angle theta with the direction of motion of this particle A, that is with the x-axis, then you can see that this particular length r is increasing with a rate of u cos theta. This velocity u is going to have two components. One will be u cos theta along this line joining AB. So u cos theta is responsible for increasing this length AB. So it will be positive of u cos theta, right? And this v, this velocity v is actually decreasing this length r. It is responsible for the decrease in this length r, which is the distance between the points A and B, the particles A and B. So that will be minus of v. So rate of change of this length r is simply we are considering the velocity component along this line AB, and the component which is increasing the length will be considered as positive and the component which is decreasing the length will be considered as negative. So u cos theta will be considered as positive and v will be considered as negative. So if I multiply this equation with dt, so dr will be equal to u cos theta into dt minus of v dt. Now remember that u and v are speed of the particle. So these speeds remain constant. So now if we integrate this equation on both sides, so first term is the integral in r. R is the separation between A and B. So the initial separation you can see between A and B was equal to small d. And when the particles will meet, the separation will be 0. The second integral is in the terms of time. So let us say the motion started at t equal to 0 and the chase ends at some time capital T. Similarly, the last term is an integral in time. So we'll integrate it from 0 to capital T. Now the first term, this becomes simply 0 minus d, which is minus of d. Now u is a constant. We can take it out from the integral into cos theta dt integrated from 0 to capital T minus this term will be again v into t. So let us say this is our first expression. Now for the second expression, we'll consider the trajectory of particle B along this path of particle A. So you will always have, that is in this question we have a particle which is moving along a straight line. So we'll consider the projection of this path that particle B has taken along this line x-axis, along the x-axis, which is the direction of motion of particle A. Now, how do you take a projection of a curve along a straight line? Simply you drop a perpendicular from the ends of the curve onto this straight line. So you see, if you drop a perpendicular from the initial position of B on the x-axis, it will be this line, right? So this is perpendicular. And already the point C, if you drop a perpendicular from this end onto this x-axis, it will be the point C itself. So dropping a perpendicular from the ends of the curve onto a straight line will give you the length of the projection of the curve on that straight line, right? Let me explain it in a another diagram. Let us say you have this straight line and you want to take the projection of this curve on this straight line. So what do? We simply drop perpendiculars from both the ends of this curve onto this straight line, right? And this particular length that you can see over here, this particular length will be the projection of this curve onto the straight line, on this straight line, right? So you can see along the direction of particle A, along the direction of motion of particle A started from this position at t equal to 0, and the particles meet each other at this point C. So in capital T time, what is the distance that particle A has traveled? It is simply the length AC. And since it is moving with a constant velocity u, I can say that this length AC is equal to u times of, let us say this is capital T. So the distance that the particle A moves along x-axis, that is u into capital T. Now, what is the distance that the particle B has moved only along the direction of x-axis? So, I am taking the projection of this curve of particle B along the motion of particle A. So, you can see that the velocity of particle B parallel to the direction of motion of A, this component is v cos theta. So, if I integrate v cos theta into dt, from 0 to capital T, it will give me the length of the projection of this curve that the particle B moves along this x-axis. Because V cos theta is the component of velocity of particle B along x-axis. So velocity into dt, this is the displacement along x-axis. And in 0 to capital T, if you take the projection, it will be from this point A till the point C. So I can equate these two terms. So ut can be equated with integral of v cos theta into dt from 0 to capital T. Now from this expression, the integral of cos theta into dt from 0 to capital T, this term will be u into capital T divided by v. Because this v is constant, you can take it out of the integral, right? So let us say this is our second equation. So you replace this term integral cos theta dt from the second equation in the first equation. You will getting minus d equal to u times of u into capital T by v minus of vt. So from here, the time after which particles will meet is v times of d divided by, it will be v square minus of u square. So this is the time after which the particles are going to meet, or the chase will end after this time. So you can see in this expression that this expression for time will hold only if the value of v, which is the speed of particle B, is greater than the speed of particle A, which is equal to u. Now what happens if v is equal to u? If v is equal to u, obviously this time is not defined, this expression is not defined. So what does it mean? That if v is equal to u, this chase is not going to end. And there will be a final separation between the particles. Chase will not end and a finite separation will remain between the particles after a long time, right? So you can try that particular question. You can try it that if v is equal to u, what will be the final separation between the particles? And we'll pick up that part in the next video.